Thank you very much. So today I will briefly report about an activity that has been going on in a group for several years now, initiated by a collaboration with Massimo Vergassola, and then further on with several other collaborators and students, former students of mine. So our interest starts from naturalistic observation. That is that there exist many birds, actually, even the humble seagull, who can stay up in the air for very long periods of time without flapping their wings. And as a matter of fact, not only that they can stay up in the air, they also can soar. So they can exploit atmospheric currents generated either by dynamical patterns of the atmosphere or by thermal plumes created by convection. So hot air tends to balloon, and birds are able to identify the regions of space where this hot air is ballooning and use it to go up in the air. So why would they do this? One possible reason for doing this is for predators to take a vantage point from high above, where then they can just dive to the ground to catch a prey. This is a typical behavior of peregrine falcons. Here you can see GPS trajectories of a peregrine falcon during a sunny afternoon, and you can see the patterns of behavior. The falcon localizes these thermals, ascending, ballooning hot air currents up to a certain level, and then it dives down close to the ground, and then picks another one, spiraling up, and so on and so forth. So falcons can do this for several hours with basically zero energy expenditure, which is, of course, a strong biological constraint for this behavior. An even more impressive example comes from migratory birds. So these are GPS trajectories taken from frigate birds. Frigate birds are migratory birds who every year undertake a travel across the Indian Ocean from Southeast Africa to Southeast Asia. They travel for about a month over the ocean. And to add even more complication to this pathway that they take, they don't like to sit in water because they don't have waterproof feathers. So they spend most of the time in the air. They just go approach the water when they have to feed. And as you can see, they take very different routes. All of them are in the direction eastward direction, but they take very different routes. And then by tracking the trajectories, this group of researchers led by Weimerhirsch were able to show that on the shorter scale, they perform a pattern exactly like the one followed by predators. So they catch up these ascending currents and then go down. And they were able, by using special loggers, to estimate that 90% of the time they don't beat their wings. So this is an extremely efficient way of going from one place to another with the least energy expenditure. I must say that it should be very clear from the outset that this is an extremely difficult task, especially over the ocean, because the time scale by which these ascending currents form and are destroyed is extremely short. It's about 15 minutes. This is just you can estimate this very simply from the typical length scale, which is set by the height of the convective layer in the atmosphere. It's about 1 kilometer, and the typical speeds. And then you come up with an estimate of 1,000 seconds. So this means that if there are convective currents, this means that the atmosphere is turbulent, and this means also that it is unpredictable, and its predictability scale is no longer than 15 minutes. But 15 minutes is exactly the time that it takes for a bird to soar from the ground to 1,000 meters of altitude. So it's just like walking from across the ocean, but hopping on stones that continuously appear and disappear. So it's an extremely dynamical, unpredictable environment, but nevertheless, birds are able to exploit this. Like I said, on the ocean, it's even more complex because you don't have very simple visual cues that you might have on ground. Okay, on the ground, it's very easy to identify regions where there could be ascending currents. For instance, the side of a hill, which is well exposed to the sun. This is a good place where to ascend. So people who do paragliding know this very well. But in the ocean, it's essentially a featureless landscape. There are some visual cues obtained by clouds, but in general, it's a very difficult task. So it's quite intriguing as a behavior. To add even more interest to this, recently there was an experimental study with condors, and they showed that their trajectory is as long as 100 miles in which condor fly without flapping their wings. Okay, so this is extremely impressive behavior, which of course motivates the question of how could they possibly do it? And if you break down this question, there are two things that you would like to know. What kind of information do they really need about the environment in order to perform this behavior? And the second thing is how this information is translated into actual behavior, into maneuvers that allow them to catch up on disturbance. So if you abstract away from the specific biological problem, which could be of great interest to ethologists and neuroscientists, but if you look at that from the viewpoint of physics and algorithms, this is a question about perception and control. So how do you deal with a system which has a limited perception, limited control, and wants to perform a very complex task? So if you go back to the basics, the classical approach to how to control a system, a dynamical system, as this is the classical optimal control theory, which in a nutshell tells you that if you are able to describe your system in terms of some dynamical system, which could be stochastic, or here I'm just putting deterministic, but there's no specific restriction to being deterministic, and you set up an objective of this form, which is a maximization of certain integral along the trajectory of your dynamical system, or the minimization of a cost, if you wish. These two languages are equivalent. Then there's a possibility of solving this problem by certain techniques, which could be analytical only in very, very simple case, but could be numerically attacked in more complex cases. So there is at least a practical route to solve this optimal control problem. What are the limitations? There are actually big limitations. First of all, because you need to know exactly what are the governing equations of your system, which in our case, for instance, would mean you need to provide knowledge about the dynamics of the atmosphere and the dynamics and the mechanics of the bird in the atmosphere. So it's a lot of degrees of freedom. Moreover, sometimes you're not even able to specifically say what are the governing equations in a very complex system like this. Okay, they might be extremely complicated to write down properly. There are two problems here. So one problem is that you, as a decision maker, as a controller, have an access to a very limited low dimensional space of observations with respect to the full configuration space of the system. And the second thing is that often the dynamics is not known. Okay, so the questions that arose earlier I would say that this field was developed in the mid to second half of the last century, 1950s onwards. So can one find the way to control a system optimally or approximately optimally without relying on the knowledge of the equations? And the second question, what is the effect of being able to observe just a limited subset of degrees of freedom? So the answer to these questions came from, so we don't have to reinvent anything. There's been a huge part of machine learning devoted to this approach, and this is called reinforcement learning. So what is the underlying idea? If you don't know the model, the dynamical laws of your system, you have to replace this a priori knowledge with some posteriori knowledge. Okay, so that's quite easy. So that's where data come in. If you can collect data coming from the environment, you can replace this knowledge with this empirical knowledge, and then you can try to solve in an approximate way the optimality equation, and that's the first thing. The second thing is that, like I said, you observe only a very limited portion of this high dimensional space of configurations. So the way to deal with this problem in machine learning in general is to use function approximation. That is to use a certain basis of function or a certain nonlinear approximator which is able to interpolate correctly your data and also extrapolate to situations that you have never seen. So these are the two key ingredients. When you come to talk about function approximations, there are two possible approaches. One is just to use what is called a linear feature-based system. Okay, so you just select a basis of functions where to expand your functions that are important, right? So you select a number of features because you have some expert advice. Okay, that's what we physicists do. We say, okay, I look at this problem, and that's what I will do in the following. I think that the relevant variables are the position of the bird in space, or the accelerations, or the relative angle of the wind. So I select a few number of selected variables, and then I try and see to optimize on this restricted subspace. Of course, this has advantages and disadvantages. If you make linear approximations, all the machine learning theoretical machinery works very well. The problem is convex. You can prove theorems, establish bounds, etc. It's easier to train, but of course, it all depends on how good was the expert advice you gave on how to select the relevant variables. So in the computer science community, there's a tendency to take the opposite approach, to rely much more on data than on prior knowledge, and to use nonlinear universal function approximators, which, for instance, are neural networks, not the only ones. They have the advantage that really they are more model-free than the way you use, so they can reach very impressive performances at the price of having a weaker theoretical status. They require a lot of data, and often you cannot interpret what comes out of them. It's very difficult to do this. So in the following, I will focus on the first approach. So very briefly, I'm just want to here demystify many of the aspects of machine learning, and in particular reinforcement learning, just to show you that the pseudocode that performs such kind of optimization is actually a few lines long, okay? And it does only a very conceptual, very simple stuff. You start, my mouse, where is it? Yeah, I don't see it. I will use this. Okay, you start out with some function which describes your expected quality of your decisions. So this function Q tells you, if you find yourself in a situation S and you make the decision A, and this function is parameterized by certain parameters W, this allows you to rank your decisions. The decisions which have a larger Q are better, okay? And you start out with some guess, maybe a flat function. Everything is totally indifferent. And then as you interact with the environment, so by trial and error, you update your function by making corrections. Basically, you compare what you get from what you expected. If you were optimistic, you reduce your expectation. If you are pessimistic, you raise them. And you use the new updated function to generate new functions. And this process, when tuned properly, allows you to converge towards approximately optimal solutions. Okay, so conceptually, it's very simple. It might be quite challenging, of course, in practice. So what we did as a first, I have to keep an eye on time, yeah, is to train virtual birds. Okay, so we set up a synthetic environment, which is made by numerical simulation of a slab of the atmosphere. Very simple model. So this is you should think of this as a cube of 1 kilometer size. We don't solve very accurate equations for the atmosphere. It's just a convective fluid here. Here you see just a snapshot, but you have to imagine that these structures here, which are the thermal going up and the other downdraft blue going down, they change dynamically and they move. Okay, I don't have a movie to show, but you can imagine easily how it is. And then we describe our birds with a very simple mechanical system, which is a rigid object, which has basically two possible ways of control its position, that is to roll or bank, so the change in inclination in the side, or to change the angle of attack. As a matter of fact, in the following, I just limit myself to doing this direction. So it's just like a bird, which is extremely naive. It just can do like this and that. And it senses some local properties of the flow. So it has no long-range perception, etc. We're going to try to train the dumbest possible bird ever to see if they are able to learn to ride thermals even under such stringent conditions. So in this particular case, what our birds are sensing is the state of the atmosphere in its immediate neighborhood. So over the scale of 1 meter. And over time scale of 1 second. So it's an extremely local information. They don't know what's happening on the scale of 1 kilometer. So how can the miracle happen? Well, this happens just because turbulence is a system which has many degrees of freedom which are coupled to each other. So the small scales know somehow what happens on the large scale. It's up to the bird to discover what is this connection between small scale behavior and large scale behavior. In particular, to connect local accelerations imparted by the wind to large scale patterns. So is this possible? And then by running this kind of algorithms, we actually see that it is indeed possible to some extent. So naive birds which start by doing quite poor performance, after several rounds, actually tens of thousands of rounds of this interaction with the environment, trial and error, and change and update your decision making, eventually are able to catch thermals and to ride them up. Okay, so I'm not going to spend a lot of time on this because there's more that I want to tell you. But the final outcome of this algorithm is actually a lookup table. It's a lookup table like this, where you have the current angle of the bird. So the bird says, okay, I am -5 degrees with respect to the ground, and I am perceiving a certain set of accelerations. Let me pass on the details. I can explain later if you are more interested. And then this lookup table tells you, okay, if you're here, further increase your bank. If you are there, decrease it. And if you are in a position where there's this orange square, you just stay in place as you are. So this simple lookup table produces a behavior that allows you to climb up by, I don't know, order of 100 meters, 200 meters when rescaled, which is far less than what real birds can do, but it's a proof of principle that it can be done based on very few inputs. So moving on, what happens if we go towards machine behavior rather than animal behavior? So this technique of climbing thermals is actually the very same technique that experienced pilots use when they fly sailplanes. So these are planes which have absolutely no thrust, and there are cross-country races that take place over ranges of several hundreds to 1,000 kilometers. And in one day, they can cover maximal distances of several thousand kilometers, again, without any energy expenditure. Okay? So what we ask ourselves is that, will our algorithm be able to discover or to rediscover proper strategies to fly sailplanes? We set ourselves to a more humble task, because if you want to try to do something on autopilot on a thing like this, which costs you $30,000 or more dollars, that's probably not a good idea. So we use the recreational toys of the size of 2 meters, which cost you $200, which is much more affordable in case you crash it. They are equipped with the remote control, so you can pick them up if something goes very, very, very bad during the training. But eventually, again, repeating a series of interactions with the environment with a slightly different algorithm, because it would require too many attempts at learning if we did it the other way. But with a slight modification of the reinforcement learning approach, we were able to train quite successfully these gliders, and they also are able to pick up thermals in much more challenging situation, because you see this is an open place in the outskirts of San Diego, so there's a lot of topographic details, and the climate, of course, the weather, of course, is much less reliable than the one that you have in a computed synthetic environment. But nevertheless, it seems that it works. And it was also comforting to discover that the kind of lookup tables that we find are actually qualitatively very similar to the ones that are known to pilots as empirical rules how to drive. So this is sort of a proof that we are looking at the right things, and that this kind of inputs are sufficient to cook up reasonably good decision making. Okay, so for the very final part of my talk, I want to change gear once more. So if you, again, distill the very basic message of this work, is that there is a way to extract energy from a non-equilibrium reservoir, such as the atmosphere. So in this case, energy in the case of birds, or is mostly converted into potential energy, which is then converted into some directed motion. But you could also ask yourself the question, can we extract energy for energy consumption purposes, for energy production purposes? So that's where airborne wind energy comes into the game. So what is it? So this is what airborne wind energy is not, and it's the usual, most common way to extract energy from the atmosphere. What are the challenges of using wind turbines? Well, first of all, these are very heavy objects. They have basically reached their limit in size. For structural reasons, it's very difficult to build wind turbines which are more than 200 meters high, whereas we know that the strongest wind in the atmosphere are about 500 meters and above. So they are sort of using just a very low level where the winds are comparably smaller. They are less controllable to an extent, in the sense that you can change a little bit the shape of the turbines dynamically, I mean adaptively, but not that much. And of course, once you put them there, they are there. They are not at all movable in any reasonable way. So airborne wind energy tries to address this problem by using, for instance, kites. Okay, so kites, of course, are very lightweight. They can be sent very high in the atmosphere, 700 meters and above, using sufficiently strong lines. They are deployable, so you can have these trucks which moves around and catches up different situations of wind. Their cost is much smaller, so they are especially of interest, for instance, to situations where you need a limited amount of powers in rural areas or in developing countries. So that's one reason why we're interested in this. They can also use for maritime transportation, by using them to help propulsion. Okay. So, and interestingly, there's a lot of room to control dynamically these objects. So just like birds, you can pull the lines and make them change one direction or the other, and have them perform some cycles, or use them to propel your vehicle. So more in detail, so this is one possible situation, ground generators. These ground generators, here there is a power station, the actuation unit is called. You have your kite. So at the beginning, this works in cycles. At the beginning, you find that the configuration of your kite by which it just gets sent out by the wind. So it unrolls the lines, and the lines are connected to some generator, which produces electrical energy. And the trick here is to do a non-reciprocal cycle, so to pull it back in a way different from the one that we went out, which you can do by maneuvering, and therefore to have a net cycle which produces energy. So very intuitively, just think about an object which catches the wind this way. So the drag will take it very far away, and this produces energy. And then you come back, for instance, by aligning it this way. And when it comes back, the drag is smaller because it's offering less resistance. And if you're able to keep it on air, because that's a challenge, because if you change the asset, might be that it falls down. So if you do it properly, you might be able to realize a cycle and produce energy. So that's what these devices are trying to do, in a way that, however, is not optimized, in the sense that they use some empirical rules and the way to deploy it in one way or another. Also for auxiliary propulsion, so there are some prototypes that actually claim that they can substitute for 20% of the engine's power in ships, which is enormous as a gain in terms of energy saving. So what we did, again, more humbly, is that we limited ourselves to, a numerical simulation. So this is another very crude sketch of what happens in the atmospheric boundary layer. At variance with the previous case, now we have a mean wind, which increases with the height. So this is what is called technically a turbulent wet flow. There's a jet stream above, and there is the ground which keeps the zero velocity. We use, again, a very simple mechanical system description of this, this really elementary, a little bit of aerodynamics here, and an object which is just carried and with some friction there, very low level description. And we provide as inputs to this algorithm the usual very simple and local observations of what the wind is at the kite's location, something that can be easily be measured by sensors on top of the kite. So again, we do the training. It takes a little bit more because the situation now is a bit more complicated, but eventually it learns to travel the maximal distance that is allowed in that period of time that we are under consideration. So this is the kind of trajectories that they show after training. And you will see that there is this recurrent pattern of helices. You can notice that helices are quite irregular because they depend on the local properties of the flow. So the system is adapting to local turbulence fluctuations. When the wind is slightly stronger, it decides to do the helix or not, depending on that. You can perform some more refined dynamical system analysis, and you will see that more explicitly that there are cycles here in which as the angle of velocity with respect to the kite changes, then the system reacts by adjusting its angle of orientation with respect to that. So these cycles are reflective of this behavior. And as a matter of fact, you can, once you understand the way it works, you can further simplify your problem and produce a very, very simple distilled lookup table, which does not have all the complexities that might emerge from the data analysis. It's just a sort of simplified, very simplified version of what the data give you. And then you test it and you find that it performs basically as well as the learned policy. So yeah, time to close. Yeah, to allow for some time for questions if there are. So what we're up to in the near future is perform the same kind of analysis for the energy production system. Also testing this against more refined machine learning techniques with neural networks, because they provide the possibility to explore solutions that maybe we are not able to see because we restrict ourselves to a very specific subspace of observables. So maybe there are better observables that are there to be discovered. One key aspect is also that it would be interesting to see both for the birds and for these devices how it's possible to use several agents learning together, maybe compensating for each other, maybe transmitting information to each other in order to optimize all these kinds of behaviors. In birds, this happens all the time. Even in the simple task of soaring, we know that griffons typically soar in pairs and they look at each other. We know this because there are people riding delta wings or I don't know. Well, they can take videos and they can look at the behavior. So this multi-agent navigation is also a task. And let me close just by advertising the fact that we have an open position on multi-agent reinforcement learning in collaboration with the Rome group to work also on experimental data of midgets and of birds that are taken by the group of Giardina and Cavagna. And with that, thank you for your attention. I'm happy to take questions if there are.
Thank you very much for this very instructive talk. So we have time for 1-2 questions. If anyone ready?
I have one simple question. So, with reference to the kite that you were mentioned, so where is the energy being actually produced? Is down? Is the consequence of the fact that the sort of cable is exerting a force?
Exactly. So maybe this sketch is the one that explains it best. So here is the schematics of the place where the energy is actually produced. So you might think that here there is just a I don't know, electromechanical system.
No, okay.
That's it.
I think I understand. Yeah. That's
Very well. Last one. If not,
Okay, thank you for the very interesting talk. So you mentioned that this environment is very unpredictable, but still, like, how robust is the result of your training? Like, I mean, you train this bird-like thing for some kind of environment, but then like you move on to some other kind of environment, and can you still expect it to perform?
That's an excellent question. I can answer to this by getting back to one previous slide, if I'm able to do this quickly enough. And that's the slide. So here we trained our soaring birds in two very different situations. One, when there is a weak convection. So the convection is rather organized in space. You have these mushroom-like structures. And then a situation where there is strong turbulence, in which instead the structure are much more difficult to ascertain. And you will see that there are differences in the policies. Okay? For instance, take this situation, which is the situation which is nearly neutral, so acceleration are more or less balanced. In this case, the low turbulence, the agent doesn't want to stay there. It just tries to steer away, probably because it thinks that there are better opportunities somewhere else. While here, it's a situation that is more challenging. It takes a more risk-averse strategy, and it says, okay, this is good enough, I'm not falling down, I'm going to stay here. So what we think is that we didn't do that in practice, but what you can do is to sort of have a system, overarching system of several possible situations, okay, which could be, for instance, low wind, strong wind, so it can classify a few sort of climate-like situations, and then let the system below decide on the atmospheric local situation. So this is certainly a good point.
Okay, thank you.
Thank you.
Okay, I have one last curiosity, if I may, about this kite technology. So are they at the moment prototypes or already scaled up to function?
Okay,
And
so
second question, very short, is this only for air or can also other currents be used, say in ocean current or something like that?
okay, very good points both. So for maritime transport, there are prototypes. So what I'm showing here is like this is an actual photo, the one that you're seeing here. So this has been really tested. So the problem of moving to commercial is quite interesting, because clearly these sails can work if you have your wind in the right direction. Okay, but now commercial routes don't follow anymore the trade winds routes. So often you have commercial routes that go up against the trade winds. So you would have to change overall the trajectories, the routes of the ships in order to be able to exploit this on a large scale. And then regarding in water, yes, there exist gliders, so-called, also for the oceanic environment.
So let's conclude with the very, very last remark over there, because it's, so are the kite and bird models treated as a rigid body or can they flex? And maybe just be short.
Yeah, that's a very good question. No, they are rigid in our approximation, so very, very limited number of degrees of freedom. But of course, it matters to be flexible.
Okay, let's move on and thank Antonio again.